Welcome everybody on Zoom. Welcome everybody in the lecture hall. So what are we going to do today? First, let's start with what we did last week. We looked into the relational model, relational tables. We defined what this means. And today will be a more practical lecture. But before we start, I would like to first ask you a question and check your knowledge of last week's lecture. So please go to this website right here or download it on your smartphone. And this is my question to you. What is a relational table? So the first answer is that it is a mathematical relation over attributes domains. The second one is that it is a mathematical relation over several sets of attributes. The third one, it's a set of relations between strings and values with monotonous supports. Or fourth one, it's a set of maps from strings to values and with identical supports. That's called relational integrity. Multiple answers possible. Normally, if I configured the question right. All right, anybody need more time or it's all good? All right, I don't see any raised hands. So let's see first what you say. Aha, there is disagreements. So where are the good answers? So it turns out that the majority is correct on one of the definitions, actually the most important definition, as a set of maps. It's just a set of maps. A record in a map is a map, and a table is a set of records. The maps map strings to values. It maps the attributes to the values. For example, first to Albert, last to Einstein, and so on and so on, right? So every record, every row in a relational table is a map from the attribute name to the value. And with identical support, what does it mean? Maybe on Zoom. Anybody on Zoom, maybe? What does identical support or relational integrity means? Yeah, we're going to say it's Friday morning. So relational integrity means that when you have this set of maps,
we have same attributes for each row.
Exactly, yes. All the rows have the same attributes. So the maps have exactly the same support. The support is the set of attributes that are associated with a value in a map. Yes, so basically identical support means that it fits in a table. If you can paste the maps together into a big table. The second definition, which you actually find in many database textbooks, which is more classical, is that a relational table is a relation over multiple domains, right? The second one is not correct because the relation is over the attribute domains, but this answer said it's over the sets of attributes. So you would be putting attribute names in relations with each other, right? But this is not what it does. And the third one is just totally made up, and I don't even think it means anything in particular. So that was just a trap. All right. Do I have another one? I told you that relational tables, in the sense as we will use them in this lecture, are a set of maps, but with constraints. Which one of these four here is not one of the constraints that we have seen, right? Is it relational integrity, atomic integrity, attribute integrity, or domain integrity? Three of them are correct. These are constraints that we have on our sets of maps. The fourth one is incorrect. Let's see live if it converges. Oh, it does converge. Now you agree. This is awesome. All right. This is correct. Relational integrity, atomic integrity, and domain integrity, these are the three. I will show it again on the slides. Attribute integrity, the attributes in a table must all have the same length? No. For example, if you consider like first, last, birth date, and so on, the number of letters in the attributes is totally different. There's no such thing. All right. So this was an easy one. All right. Let's now move back to the slides and get going. So, as we said, 3 integrity constraints on relational tables defined as sets of maps. Again, the visuals of them. First, relational integrity means that it fits into a table. This is what we called structured data, right? This is a counterexample. This is a huge mess, right? This is missing, this is missing, this is missing. Here we have an extra attribute in this third map here. So you see, this is just not respecting the relational integrity. You can barely make a table out of that. So this, yes, this, no. Atomic integrity means you cannot have tables in tables in tables in tables. All the values that you have must be simple values, atomic values. Strings, integers, dates, that kind of things. We'll cover that actually today more in details. A counterexample is like this Inception movie, a dream in a dream in a dream. You cannot have a table in a table in a table. This here breaks atomic integrity. We will not have this in our lecture. This is what tables will look like. Third, domain integrity means that every attribute has a domain. A first name must be a string, a birth date must be a date, and so on and so on. And we must respect this. For example, integer for the year, these are all integers. Here, these are Booleans, true, false, and these are strings. All right, this is broken. Why is it broken? Because with respect to this domain right here, this is not a Boolean, this is not an integer. You probably have the intuition on how to fix this, right? Probably you're going to put false in here and here 1931, for example. But this is not going to happen automatically with a classical product. This is something you have to do yourself, right? This sort of data cleaning is actually extremely important whenever you do machine learning, for example, because the data sets are usually going to be a bit messy, right? So it requires a bit of cleanup, but now there's plenty of products that help you clean up your database. Okay, domain integrity, atomic integrity, relational integrity. If we have the 3, we are in the relational table domain with SQL. Do we have a question?
Yes. How would you go about having a table as a value? Say, for example, if you want to represent a student, student colon weekly schedule data set. So the weekly schedule for a student. Would you just have a pointer to another table instead, or of the table itself? Or a table in the table itself? Is that allowed?
So that's a good question, and this is also part of what we will discuss in this lecture. So there are actually 3 ways of doing that, of storing this kind of data. Table in a table is one way of doing that, right? It's just that it breaks atomic integrity, so that would be over here. You would have a table in a table. So we are not really going to do this in our lecture. The second way to do it is to have several tables, and to have the tables pointing at each other. We will in fact cover this today, or at the latest next week if we have time. So I'll show you how you can have a table point to another table. And the third way is to duplicate data. You can actually have repetition of the same data on multiple rows in order to replicate what the other table is. This is not a good idea in classical databases. I will cover that actually in database design theory, so I'll come back to that. But in big data, you do that. Duplicating data is fine because it makes it faster, right? Did I answer your question? That was a good question.
Yes.
Okay. So quick reminder, a relation between two sets looks like this. You have a first set, you have a second set, and you can map the values to each other without any restriction on how many, right? So you can have 0, 1, 2, so this is 2, this is 1, this is 3, this is 0, and the same here. Here you have 3, here you have 1. So this is a relation. That's the most generic thing you can do. A map is a restriction of that disallows more than 1. You can have 0, you can have 1 row coming from every node here, but not more than that. This is not allowed in a map. This is not allowed, right? So in our case, a map is a record in the table, so we can map at most one value to each attribute, and these are the attributes that are not part of the map. They are not in the support, so they don't even appear in the table. Then you have functions. A function is exactly one here, exactly one here, exactly one here, exactly one here. We'll see functions again in database design theory because we study functional dependencies within tables. This is also a discussion related to the questions the question we've just had on Zoom. Okay, so we have these two definitions. The typical textbook one, a relational table is a relation over the attribute domains. It's a subset of the Cartesian product. That's why it's called relational. Or you can define a relational as a set of maps from strings to values and with identical supports. This is the fancy notation of that. And the idea is that in the textbook definition, you basically get relational integrity and domain integrity for free. Not atomic integrity though, but relational domain integrity is for free in this first definition. In the second definition, you get relational integrity through the constraints of the identical support here, but domain integrity is separate because here I don't say what the domains of the attributes are, right? So this is a separate definition. And furthermore, the first definition is imprecise for all kinds of reasons, and some of you actually noticed, for example, if you do define a relational table as a relation over domains, the problem is that it creates an order on the columns, but you do not want an order on the columns in a relational model, right? So it has this sort of issues. Another issue is that the columns are identified by numbers, first, second, and so on, but we want to identify the columns with names. So this is why using sets of maps, we are actually using the attribute names to associate them with values, right? So this is why I use the second one. And the advantage of this second definition is also that the transition to big data is much easier, because what does it mean to go to big data? You just drop the three constraints and there you go. A set of maps is basically a big data collection. Right. Okay, so this is what it looks like with the maps, right? And we call extension the set of maps, right? And the attributes are typically separate. This is what we call a schema also. And we add on top domain integrity. So typically when I draw my diagrams, I will add an extra row below the attributes. This is not an actual record of the table. It's just where I put my types, my domains, right? So integer, Boolean, date, and so on. And then I have my extension. And so formally t.a, if t is a record and a is an attribute, then t.a, which is the value at that position, must belong to domain D, all right? And then with relation, it would be that you take a set of schema attributes, the domain, and you compute the Cartesian product. Okay. Now in practice, I gave you this definition so that formally we have established what a table is. Now, of course, when people manipulate database products, database systems, they are not going to think in that way. They are not going to pour mathematical formulas all over the place, right? So what we are going to do today in practical terms is really look at tables like that, you know, in a very simple manner and reason with them. But nevertheless, having the formalism is actually very, very useful. All right, having said that, now we are going to start with the new material. I'm going to start with SQL. SQL is a language, it's a query language. It was actually developed at IBM, so mainly these two persons, Don Chamberlain and Raymond Boyce. I didn't find a picture of Raymond Boyce. Unfortunately, he's no longer with us, but his name will appear at plenty of places in the lecture because he gave his name to one of the normal forms that we will study in this lecture. So Boyce, you will see that name again. Don Chamberlain is very active also in big data. For example, he was when we worked on Xquery in the working group. He was also in this environment. So yeah. Then the early days. So this is the 1970s. I told you Edgar Code suggested data independence in 1970. So that was the formal thinking. And then what happened is that it became a business, right? So it's like today, what you do at ETH, right? You work on a project, maybe I was a PhD student, and then you create a spin-off and you try to make it grow. So the same happened back then, right? So the idea of data independence was new. And so the first commercial relational database that tried to implement this idea of data independence was called System R. Probably R is for relational. And the SQL, SEQL, was the first commercial relational query language that was used in order to query the tables. Pratt & Whitney, that you see here at the bottom, was their first customer, 1977. So you see it took 7 years to go all this way. Okay, so what is SQL? It meant structured English query language. Why do we need a language like this and not Python? So of course, Python didn't exist back then, right? But why not a language like Python or like Java or like back then COBOL, Fortran, and so on and so on? The goal of the language was to be natural, just as natural as a table. It has to be declarative in the sense that you should just say what you need, but without actually telling the computer how to compute it. This the computer will figure out. So it's a declarative language. And the second property of SQL is that it is set-based. When you have a language like Python or Java, you manipulate one thing at a time. Each variable in the language contains one thing, one object, one integer, one string, right? Not so in SQL. In SQL, what you manipulate is an entire table. It can be thousands of rows, millions, billions, trillions today, because SQL is also used on big data, and in a single value, like a single expression, a single variable, so to say in SQL, is going to be potentially a huge table. So this is what we call set-based, but it shouldn't really surprise you because we define the relational table as a set of maps. So the fact I'm saying it's set-based shouldn't really surprise you, okay? Now, a clarification of why I keep saying SQL, but it's written SQL, is that they had trademark issue. So SQL was apparently already in use somewhere and they sued. So they had to change the name and they just simplified it to SQL, Structured Query Language. But all of the people who were around at the time kept the habit of saying SQL. And that habit actually keeps being transmitted from generation to generation of database people, me included. So this is why I keep saying SQL. But you can also say SQL if you want. Just do not be surprised between the two. It's really the same thing. Just as a general impression, who here says SQL? Okay, on Zoom, how does it look like if you raise your hand? I see. Oh, it counts even. We have 2. Raise your hand on Zoom if you say SQL. 6, 7, 8, 9, 10, 11 keeps going up. All right. Okay. Now, who says SQL? Less of you. Okay, and on Zoom, who says SQL? Okay. Is it because of me that you say SQL? Is it because of me or you heard it before? Okay, so some of you, it's because of me, some of you, you heard it before. Okay, anyway, but we clarified it's the same. SQL, SQL, you don't need to distinguish. All right. But SQL is a big language. It's easy to learn, we will see. But so far, we are not going to manipulate tables just yet. Because we have yet to see the theory of manipulating table, which we'll do next week. But what we've seen so far in theory is what a relational model is, what a relational table is. So we'll see in how in SQL you can create tables like that and populate them. So the first thing we need to know and to study is the types. So far, I haven't really said much about the domains. I just told you, you have domain integrity. You can enforce that in the same column, all the values are in the same domain or they have the same type. I gave you a few examples, integers, Boolean, strings, dates, but we didn't go in details. Let's go in details now of that, because when we have Postgresql, which is an actual product, there is a documented list of domains that you can use, right? So we are going to basically do a survey or an exploration of all of these domains, and I'm going to give you the actual names that they have in SQL. So you see, we are going to see strings, Booleans, dates and time, numbers, duration, enumeration, binary, and so on. And so on. Okay, let's start with strings. Who has an intuition of what a string is? And I see a few hands on Zoom too. Who doesn't know what a string is? You all do? Okay, I'm going to explain very shortly then. A string is just a sequence of characters, right? And it's stored as zeros and ones on the computer, but it's a sequence of characters. So ETH Zurich, it's the Nach, which is one of the famous pieces in German. And you see that very often we put these double quotes on both sides. It's just to, you know, to say when it starts and when it ends, right? But the quotes are not actually part of the string. So what it is really, as I said, is just a sequence of characters. So foo is F-O-O, Zurich is Z-U-R-I-C-H, and so on and so on. So that's a string. Now, what kinds of strings or what kinds of types of strings can you define? Well, first, you could have fixed length strings. This is very useful, for example, for the Swiss cantons. If you want to have in a column the canton, that's 2 letters. So you can say, okay, that's a string of length 2. ZH, HG, GE, and so on and so on. So the Swiss cantons. A second way of defining the strings that you allow as a domain is a variable length. So you let it be elastic, but with a limit. An example of that is for international country codes on the license plates. Some of them are on 1 letter, like Germany, D, France, F, and so on. Some of them are on 2 letters, like GB for the UK, CH for Switzerland, EIR for Ireland, and so on and so on. So in that case, probably you want to set a limit of 3 and allow for that. There's all kinds of standards, right, for that. You have actually 2-letter country codes, 3-letter country codes, you have the license plate country codes, and so on and so on. Okay. Then you have the variable length without limit. It really means that you allow for any string, arbitrarily long. Of course, as you can imagine, everything within reason, right? Because it still should fit on a computer. And if it's very long, then you will have issues storing it. We'll talk about that in a few weeks. But for example, an example of string without limit is if what you want to store in your table is the content of a web page or a blog post. In fact, this is done. Who knows? I think it's WordPress, right? Who knows WordPress? Who uses WordPress? Some of you. WordPress actually uses a relational database behind. And in that relational database, there are columns with that type where you actually store the content of a blog post. This is exactly what it does. Okay. So now I'm using this fancy font on the right. These are the actual names of the types that you can use in SQL. In the case of fixed length, you can say character 10 for a length of 10, char 10, or just char if it's just 1, for example. For variable length with limit, you can say character varying if you like to write a lot of 10, that's the maximum length. Varchar is the shorter way of putting that, so varchar 10. And variable length without limit, you can just say text, or varchar without anything, or club. Club means, does anybody know? It's character large objects, right? So now you must be confused because why? I mean, I defined 3 kinds of types, and now I'm throwing all of these names at you, like all these various ways of doing that. It's really like Swiss German. in Switzerland, people, you can speak Zürichdeutsch, Baseldeutsch, or Schweizerdeutsch, Welschdeutsch. I speak Welschdeutsch, probably with my accents. But basically, every dialect is completely different. And people don't speak in the same way, yet we understand each other. SQL is a little bit like that. There is a SQL standard that, that people are supposed to follow, but every product has a dialect of SQL. So they will change a few things, like you don't use the same words at all the places. It's the same here. You don't use the same words for the same types. All right. So we are using Postgresql as the product. The main reason for that is that Postgresql is probably one of the database products the closest to the SQL standard. Pedagogically, this is really one of the best to learn with. It might be that later you're going to use another one, maybe IBM, Oracle, Microsoft, MySQL, SQLite, and so on. It doesn't really matter, right? Once you've learned it, you can always adapt to another one. But PostgreSQL is probably the best way to learn. So I put on the right in bold the main ones. Usually the ones you will see in practice, probably you will see char and varchar because these are the convenient, shortened way. So varchar, you will very often see varchar 255. That's a very common one. It's because many database products use 255 as the maximum parameter that they allow for varchar, right? So if you want an arbitrary long one, you typically pick this one.
We have a question. Speaking of languages, does SQL distinguish between Unicode and non-Unicode characters?
It probably supports Unicode by now. Distinguish, I'm not sure what you mean with distinguish. So the notion of Unicode, not Unicode is a standard thing. It's about how you encode characters into bits. But in order to encode characters into bits, you need two things. First, you need to map every character to some integer, which is a code. Unicode, in fact, does that. It says, for example, character number 22 is a space, for example. I don't know them all by heart, of course, but this is the idea. So Unicode is a gigantic catalog of characters. By the way, nowadays you have plenty of emojis all over the place as well. It's actually being standardized a lot these days. So it's an enormous catalog, but every single character gets mapped to a number. The second part of that is to map this integer to zeros and ones. And this is, you probably heard UTF-8, UTF-16, so these are actually encodings. Today, it is highly recommended whenever you write a computer program or write any software that you use something based on Unicode, right? Because it's international, it's easier to handle with languages all around the world. All the languages are covered, all the characters in Unicode, they keep even adding those that they find missing. In the good old days, we had ASCII in the early computers, but then it was only English characters, so it doesn't go very far. Then we had some extension of that in various ways, depending on the region of the world, but Unicode really unified everything. I'm pretty sure that PostgreSQL supports Unicode, but can you specify what you mean with distinguishing, maybe? So basically,
if it's okay, I'll just speak up.
Yeah.
On Zoom. So basically, I've heard that when you kind of like set a domain in a table, that you can basically distinguish between Unicode and non-Unicode characters, and saying that, for example, that Cantonese or Japanese signs, which are non-Unicode, that they kind of like get excluded when you kind of like set it to a certain domain. That's what I mean by distinguishing.
I see. Okay. So I'm not an expert on that. What I can do, if we take a note of that, is maybe look a bit more into this aspect of PostgreSQL, and then I come back. Maybe I can come back next week and say a few more things on that. I'm really not an expert on the matter. I'm not sure if that's the answer you expect, but I'll come back on you, right? All right. But nevertheless, I hope that what I told you about Unicode to give you the context is helping. Okay, so here are, glad it does. All right, so we have here a table with 3 columns where I gave you examples. So here it's exactly 3 characters. Here it's at most 5 characters, and here it's an arbitrary number of characters. This is new, actually. In the early databases, you didn't have this possibility to have an unlimited number. So now let's try to insert these things right there. So first, if you insert nothing, if it's exactly 3 characters, it's just going to put 3 spaces by default, right? Here it's nothing, here it's nothing. If you have 1 character, it will add 2 more spaces there, it will accept it. Here it's just going to have 1 character, F, and here just F. Foo, it's accepted here as exactly 3. Also here it's less than 5, and here. Foo bar will be an error. You see the benefit of a relational database system. It will not let you do that. If you say at most 3, then this is refused. Here it's 6, so this is also refused, and here it's fine. Then if you have spaces there, it's a bit lenient to you. So if you have spaces, it's just going to trim the spaces here, right? So FO are real characters, so to say, and it's trimming the spaces here to 5, and here it keeps them. Okay. So the best choice usually when you have a table for most purposes is to use varchar. Varchar 255 if you're not sure, or any number. Text is not really fully standard. It's also a bit less efficient. In databases, we'll see that there is a cool implementation called Toast that actually slices the strings in the relational database. But varchar is really the recommendation. Char eats up space because it's fixed length. So it's really going to use, it's wasting a lot of space basically for all the unused characters. Great. So varchar. Yes? Oh, this is what I mean with the waste of space. In char 3, this is really consuming the 2 spaces in memory. It's a fixed length of 3. In the varchar, it's not going to waste that space. It's more elastic. So it's not going to actually store extra spaces if it's less than 5. That's why I put it that way. So if you do a query later, we'll see that in 2 weeks, and query the content of column A, you will receive, in the first case, a string of length 3 with an F and 2 spaces. But if you query column B or C, you will just get 1 character, which is F. That's the difference. It's actually also to, I would say, to make it predictable for the database system. Excuse me. Irritated. Okay. So in a database, you optimize things. So you don't know in advance what there is going to be in a table. And if you give information to the database system, it can organize the layouts, the physical layout of the table and the execution of the queries in a more optimal way. So telling the database system, in column B, you're going to have a string, and I promise to you that it will never be more than 5 characters. This is very useful information for the system. If you don't provide this and say it's text, then the system must be ready to receive arbitrary long strings, and it will maybe forbid itself from making such and such decisions just out of fear that one day there will be a very long strings. That's basically the idea, right?
There's another question on Zoom. Except from wasting space, it also changes the content by adding the space character, right? And I believe the answer is no, it doesn't change the content, it just wastes the space. So I think
exactly.
The question is, the question is whether the value in this cell changes if that happens, and I don't think that's the case, right? The value that...
Well, it changes in the sense that you have 2 more spaces.
But those don't appear if you query that.
And you see, I think if you query them, you see them.
Okay, maybe
in the
wrong.
case of char.
I'll I'll defer to you.
We
You may
can
be right.
take that. I could be wrong. You know, I'm open to being wrong. You know, that's also a way of telling you can make all the mistakes you want, because also I make mistakes. So it is absolutely possible.
I'll try live on
and we will
Postgres.
investigate. Yeah, so we'll investigate that, and we'll tell you next week. Is there another question?
Can you say a string has to be at least X number of characters, for example, for website passwords?
That would probably be separate. I guess you could do that as an additional consistency constraint. I will tell you how to do that a bit later, but not as a type directly like this. I don't think it exists. Yes? Mm-hmm. Yeah, so that's a good question. In fact, these sort of questions are exactly the sort of questions that the people who implement these databases and also the people who develop the SQL standard discuss. And probably they ask themselves that question: should we truncate, or should we just not truncate? And every time the answer to that question is pragmatic. They ask themselves, how is it going to feel to the user in the end? And if they made the decision to throw an error instead of truncating, it's probably they thought that the harm of silently truncating would cause a lot of damage. Because imagine that you're storing important data in there and it's truncating without warning, then this is risky. So I think this is probably why they made the decision that way. Right? Let's go ahead with numbers then. So let's start with integers. Mathematically, it's just the set of integers is called Z, so it's a ring with addition, multiplication, and so on. So 0, 1, 2, -1, -2, and so on and so on. However, we are using computers here. We cannot just talk about numbers like mathematicians would actually do. We need to store these numbers on a machine. We need to print them on our screen. And what we print on our screen is actually text. It's actually strings, in fact. It's called the string representation. So even though we are looking at numbers, we still have a notion of lexical value or literal. It's actually the idea, you know, of writing a number, for example, in base 10, as we do today, right? So if I say 16, it's 1, 6, right? So this is a lexical value. 16 in itself is not inherently in base 10, right? It's just a number of apples, right? But in the lexical space, you actually use digits to write it. So whenever you have the notion, let's call it the notion of oneness, so whenever you count one object as the cardinality of a set, you can represent it as the symbol 1 or 0, 1, because the leading 0 doesn't change it. So this is the notion of 4-ness, like when you count a set with 4 elements, you can represent it with 4, 0, 4, 1, 0, 0. If it's in base 2, that would be 1, 0, 0. So the B just says that it's in base 2. So you see, this is the lexical space. This is what appears on your screen. So you always have to keep in mind that when there is a type, there is this abstract notion of number, 1, 2, 3, 4 as numbers, and there is what we see on our screen, which is the lexical representation. So this is important. And because of that, we have to be careful, because the length of that representation actually matters, because it eats space on the disk. It eats resources. So this is why we traditionally have in many, many languages constraints on the size of that lexical representation in base 2. This is why we typically have a type on 8 bits. It means that it uses 8 zeros and ones in base 2. We have one constraint on 16 bits, 32 bits, and 64 bits. I would say until 10 years ago, 32 bits was dominating, right? Even the YouTube counters were limited to 32 bits until the Gangnam Style video actually made its debut there, and they broke the counter. There was not, the number of views just broke the 32 bits limits, and they had to migrate the whole thing to 64 bits. 64 bits, I think we can survive a few centuries like that with the counters, because you see that that's the interval. 16 bits, you can count. One of the bits is for the sign. So you can count between minus 32,000 to plus 32,000. With 32 bits, you see that's 2 billion If you go to the positive, it's 2 billion. That's less than people on the Earth, right? So you see how it can break. And 64 bits, I don't even dare tell you and read that number, but it's basically around 10 quintillions, right? It's going to be 18 zeros. Okay, so you see 64 bits are pretty common nowadays. Okay, now these are the names. We call the 16 ones small int in PostgreSQL, integer or int for the 32 bits, and big int if you want a 64-bit integer. Here too, the choice depends on your knowledge of the data you're going to put in there. If you want a video counter, you should use big int. What you want to do is, I don't know, count the number of rooms at ETH, probably you're safe with small int. Okay. So that's the binary numeral system. I don't know to tell you much about that, but basically in the end, it's going to be written in a binary form. It's just like base 10, except that you only have 2 digits, 1 and 0. What if you add a period, a decimal period? This is then called a decimal number. Not a real number, because a real number actually can have an unlimited number of digits, but a decimal number is finite. So what you have is called a precision. That's the total number of digits that are significant. In that case, we have 32 of them, if you count them, right? I think these are the digits of pi, but I moved around the decimal period. So this is a precision of 32, and it stops here. You know, this is really the end of the decimal value. On the right of the decimal comma, here, the decimal period, this is what we call the scale. So we have here 22 digits after the decimal period. So we say it's a scale of 22. In modern systems, especially mathematical computational software, we actually can support now any precision and scale. You know, you have elasticity and can store anything you want, but you need to understand that this is not necessarily efficient, because this takes a lot of resources in order to actually manipulate these numbers. But they are supported. So you can use numeric and decimal if you want to do that, and you can have as much precision as you want in there, but again, use with caution. You can limit the precision. This is again the same as the answer to your question on varchar, is that if you have the knowledge that you don't care about more than this number of digits, then you can actually specify it, and this is going to be faster because the engine will optimize and it knows it can save space. And you can also say what the precision is and the scale, and limit the number after the decimal period in that way as well. So you see, you have a way of configuring that system. So this is another example. You can take a look offline and play around. There's also a few unknowns in there on the behavior, but I will let you do that as an exercise. One of the main differences is that it will not truncate a string, but it will truncate a number in some cases, especially after the comma, because here it's no big deal, right? You just lose a bit of precision, but it's not like truncating a string. So yeah, I will leave that to you offline. Okay. Now, if you actually process numbers in that way, that's tough to implement. It can be not very efficient. And for this reason, a few decades ago, engineers invented a standard for representing that sort of numbers on just either 32 bits or 64 bits. This is called floating point arithmetics. The way this is done is that you convert the number you want to some power of 2 or some power of 10, depending on what you want. Here it's a power of 2. And then you multiply it with what is called the mantissa, or significance. And then what you do is that you encode the exponents on some bits on the left here, and then you encode the mantissa on the right, and then you can read back the number. But of course, as you can imagine, there's a limited number of bits, so you have a loss of precision potentially, right? So this is called floating points. You don't need to understand the detail of that. It's really not expected. You should just know that they exist and they are super efficient. This is something the CPU in the computer can do very efficiently, because this fits on the registers at the CPU level. So 32 bits gives you 7 decimal digits of precision, and limits the powers of 10 to this, because in that standard, it's using powers of, oh, is it actually user? Basically, let me tell you why I don't know. The standard actually has all variants. It has a flavor with powers of 2. It has a flavor with powers of 10. This is why. All right, let me just continue that after the break, right? And then we'll look into plenty of other types. See you in 15 minutes.